So we'll begin with talking a little bit about the background and motivation. So there's been an increasing number of publicly available data sets shown marked clinical impacts on assessing anatomical structures. These include both organs and tumors. And while the amount of public data has become more and more widely available, these imaging data sets still are too small for the development of robust AI models. Likewise, there's a large difference among the data preparation methods, as well as the fact that traditional approaches for these model developments are usually kind of a one-one approach, one model, one task. The authors here propose using CLIP, or contrastive language image pre-training, to accomplish segmentation tasks utilizing multiple data sets as opposed to one. CLIP was developed by OpenAI to aid in connecting images and their textual descriptions. So you're training the model essentially to recognize these matching image text pairs and learn more meaningful representations of the data itself, as opposed to evaluating these non-semantic relationships. You're actually looking for semantic relationship here. So when we think about it in the terms of image segmentation, we're adapting CLIP to look at the relationship between the imaging and the target, as well as the particular annotations such as tumor regions or left ventricle, so on and so forth. This kind of addresses the issues that we would see when attempting to collate these partially annotated data sets. Primarily, we would see label inconsistency as well as label orthogonality. So label inconsistency is going to occur in a number of ways within the data. So specifically index consistency, meaning that the same organ can be labeled across different indices across data sets, as well as name inconsistency. So specifically, in some data sets, we could have anatomical structures labeled as one thing, and while not incorrectly labeled in another data set, could just be using a different terminology. So the example that was given specifically was comparing the terminology inferior vena cava to post cava. Both refer to the same particular anatomical structure, however, labeled differently amongst data sets. Finally, within the data sets, we also have what's called background inconsistency, where an organ can be marked as background in one data set but foreground in another. So moving forward from that, we would have what's called label orthogonality. And that's essentially just referring to the fact that most segmentation methods trained with these one-hot labels don't actually capture the semantic relationship. So as previously mentioned, that's what we're actually trying to do here. So there's a possibility for extension onto more classes. So for tackling label inconsistency, the authors propose utilizing a revised label taxonomy for the multiple public available data sets. They generate binary segmentation masks for each and then compute loss only for the classes with available labels. And then in tackling label orthogonality, they're going to replace those one hot or the few hot labels with text embeddings that are going to be generated by CLIP in aims to capture the relationship between organs and tumors, also allowing for this open vocabulary segmentation, and furthermore makes it possible for extension of the model to new novel classes without forgetting previously learned classes. So here we can kind of see in figure 1 the intrinsic semantics that are involved with the anatomical structures, with those that have similar concepts within the embedding space. So for example, we have liver having a large similarity to liver tumor, as well as hepatic vessel. For those of you that don't know, the hepatic vessel is going to be what actually returns low oxygen blood from your liver to the heart. So there's a high anatomical relationship there. Likewise, if we look at the left and right kidney, we also see a large similarity present there. So for the actual training of this approach, the authors used 14 data sets presented here, as well as some additional data sets for the actual performance of organ segmentation and tumor detection. Likewise, you see 15, 16, and 17 here are actually used for the generalizability, transferability to evaluate the model. So for the large-scale private data set, so number 17 here, the Johns Hopkins data set, that is consistent of 5,038 CT scans with 21 annotated organs. And this was to investigate the extensibility to new classes that weren't previously there. So within the proposed framework, there are two main branches, the text branch and the vision branch. So the text branch is going to be what is going to generate clip embeddings for each organ and tumor, utilizing these medical prompts. So the prompt is quite important in the actual performance of the model. So if we take a look at table 2 here, the dice score starts to increase significantly. Say if we describe it as a photo of a particular class versus a computerized tomography of a particular class. So it is worth noting that that prompt is going to be very important. So likewise, we're also going to encode these hierarchical relationships among the organs and tumors. And then this branch is also going to be what's going to allow for extension into new classes without affecting those previously learned. And then in our vision branch, that's where we're going to do our pre-processing of CT scans, as well as processing of image features that are going to be extracted by a vision encoder, and then utilize the text-driven cementer for our actual class predictions. So label inconsistency is going to be addressed using that masked backpropagation technique. So essentially, we're utilizing a binary cross-entropy loss function for supervision, and then masking our loss terms for classes that are not present in the data set, as well as this is going to help with ensuring accurate supervision and update our overall framework effectively. So this is going to help in overcoming the challenges that are going to be posed by those partial labels. And ideally, the authors hope to lead to improved performance. So in terms of the model implementation, the universal model that is presented here is trained with the Adam W optimizer with a warm-up cosine scheduler of 50 epochs. The segmentation experiments done here use a back size of 6 per GPU and a patch size of 96 times 96 times 96. The default learning rate for these implementations are 4 e to the -4 with a momentum of 0.9 and a decay of 1 e to the -5 on multiple GPU. The framework is implemented on Monet 0.9.0. Likewise, with the implementation, 5-fold cross-validation is performed. So the best model is going to be selected from each fold. So the selection is going to occur based on the metric utilized. So either dice similarity and or a normalized surface distance. Now beginning to look at some initial results from segmentation, we compare the universal model against SWIN unit R, and we can see that over a variety of sites, the universal model does outperform this SOTA model substantially. However, this isn't the case in all instances. For example, with lung tumors, the SWIN unit R does do slightly better than the universal model here. There's overall better segmentation performance, though, that occurs and does offer a substantial improvement, specifically in the task of liver tumors, pancreatic tumors, and colon tumors at 14%, 8%, and 11% respectively. And then likewise, evaluation on the BTCV validation set, kind of looking at benchmarks there. The models looked at here against the universal model were all trained utilizing the same conditions to make a fair comparison. And we can see that the universal model is going to overall achieve the best performance with about a 3.5% dice score improvement over standard state-of-the-art methods. Now kind of looking forward at the tumor detection possibilities of this model, we can see that the universal model overall has better specificity in each of the tumor examples here. So with the CT scans in LITS, KITS, and MSD, those are going to be containing of liver, kidney, and pancreatic tumors, respectively. However, we do notice that for each of these examples that the overall sensitivity in each of these does not, is not outperformed by the universal model. And then to kind of look at some qualitative examples, here we see some pancreatic tumor detection examples. So in comparing the universal model to other models available, we can see that even visually, in essentially all instances, the universal model is most reminiscent of ground truth. So it is also, good to note here that the universal model is able to generalize well within this ordering segmentation, and it's not generating many false positives of tumors. And for other examples, I refer the readers to the appendix. So now moving on to the evaluation of generalizability on external data sets. The authors utilized two data sets here, the 3D IRCADB, as well as the Johns Hopkins Hospital data set, which exposes classes that aren't necessarily included in the beginning. And to look at this, we look at the mean dice score for what's there to see how generalizable the universal model is. And when we compare amongst varying classes here, we can see that in almost all instances, the universal model produces the best dice score amongst other nets that are tried. And then likewise is also coming out with the highest mean dice score here, showing a very nice generalizability of the proposed framework here. So finally, we look at some interesting properties of the framework here. Starting with, we look at efficiency in comparing the floating point operations per second versus the dice score of the models. So we can see here the universal model by far performs the best over the other presented models here. And this is looking at the number of parameters. So the circle size within the graph actually refers to the number of parameters that are there, as well as operations performed and the overall dice. So if you're up in this higher left-hand corner, you're overall more efficient than if you were in the bottom right-hand corner. And then kind of moving forward, we also look at the transferability of the models. So we do this by fine-tuning performance. So the universal model is going to significantly outperform other iterations by learning from scratch in terms of downstream data sets. This demonstrates a nice example of model deployability for outside tasks. So now in conclusion, the authors have presented a model framework for organ segmentation and tumor detection, exploring the potential of these AI models utilizing assembled data or collated data. With this, they were able to kind of tackle label inconsistency and orthogonality by extending this framework to utilize clip embedding, allowing for the ability to utilize partially labeled data sets, and demonstrated that the proposed approach is not only effective, but efficient in performing its job. Finally, noting that overall, the efficiency of the model is 6 times faster than the next comparable model here. So overall, in evaluating this paper, the authors have proposed a very novel implementation of CLIP for utilizing partially labeled data sets and tackling previous mentioned problems. While the writing itself within the paper has some minor grammatical issues, I don't believe that significantly takes away from the potential clinical application of an AI model such as this. Therefore, in rating it, I would rate it a 2 So I would accept the paper with minor revisions, specifically focusing on the grammar. And then for final publication, I would recommend that the majority of the appendix figures actually become part of the main paper. I feel as though they are not as utilized and or useful sitting in the appendix. Furthermore, another implementation that I think would be interesting here is utilizing an approach like this in immunohistochemistry staining to segment populations of cells to help to evaluate the dynamics of these cell populations on a molecular level. So while this framework has provided a very nice foundation for application of quick imaging, analysis and segmentation and detection, it would be interesting to see how far this can expand into smaller subscales and potentially help to elucidate underlying disease dynamics.